Today we're going to finish section 1.2, and we had gotten to the idea of, gotten through the idea of looking at geometric sequences and arithmetic sequences. We talked about Fibonacci sequence, and we looked at some others that are sequences that don't have any of those kind of patterns that we kind of just deemed as neither for the moment. The other type of thing we're going to look at in this section are called figurate numbers. These are based on geometric patterns, and they provide examples of sequences that are neither arithmetic nor geometric. Such numbers can be represented by dots arranged in the shape of certain geometric figures. So these are triangular numbers. So this is the picture that goes along with it. You can see what's going on here, right? If I asked you to draw the next picture, what would it look like? What would the fourth one in this sequence look like? Can you describe it for me? Right, it would have 5 across the base. Let me make that a bit thicker. And then what would it have? 4 on top of that, sort of offset, right? And then 3. And then 2. And then 1. And what if I want the one after that?
6, 5, 4, 3.
Yeah, we'll do 6 across the bottom. 5, 4, 3, 2, and 1. And we could do a 7th one if we needed to, right? In the sequence, or so it would be a 6th one in the sequence with the 7 dots on the bottom. All right, so taking a look at this, this says it can be written numerically as 1, 3, 6, 10, 15. What are those numbers coming from? The total number of dots. Now, we can count the dots in the 2 that we just created. How many dots are in this third one, or this first red one that I created, which is the 1, 2, 3, 4. It is the 5th one in the sequence, so the 7th was actually right when I said it before. What is this one? This one's the 15? Excellent. Then what's the next one? 21. Now, did you really need to count the dots? I know most of you did, but think about another way to do that. What could you do?
Add the number of base.
Right, the number of the base number of dots is the only thing that changed, right? The first 5 rows actually stayed the same. We just added an additional layer on the bottom of 6 dots in this case, right? So also we could take a look at this and notice that how do I get from 1 to 3? Add 2. How do I get from 3 to 6? Add 3. How do I get from 6 to 10? Add 4. 10 to 15? 15 to 21? Add 6. And the reason that's happening is because of that layer on the dots on the bottom that we're adding onto this. The reason I mention it, though, is because if I do that, I can continue this pattern pretty easily without drawing any more dots, right? What would come after 21? 28, because you would have added 7. And can we do one more just for fun?
36.
Is it 36? Does everybody agree? Because you would have added 8. And we could keep going. This is not, I mean, this is definitely a pattern, right? But this is not an arithmetic pattern. What makes this different than the arithmetic patterns that we were looking at last time? Right. An arithmetic pattern has to have a constant number down here. It was the common difference, all has to be the same. So all of these would have had to be the same number. And these numbers are increasing 1 every time. So it is not a constant number on this one. Okay, so this is an example of a pattern of a figurative number, and these are triangular numbers. Let's do square numbers. Sorry, my pictures don't look very square. But I think you've got the idea of what's going on, right? So take a look. The first one's got 1 dot. The second one has 4 dots. It's forming a square. The third one forms a bigger square, right, of how many dots? 9. The fourth one forms an even bigger square with how many dots? 16. So what would I do if I wanted to have the next square? I'm only going to draw one of these, but what would the next square look like? It would have 25 dots. How did you come up with 25, Audrey? Right, so you're looking at this as though you're increasing the dots on the rows and the columns by 1. In this case, it'll be 5 because the last one had 4. That looks terrible. Let's try one more time on that. I'm sure yours look much more like squares, don't they? Oh, I've got some faces, maybe they don't. Use your imagination and we'll say it's a square. All right, and so Audrey already told us that that has 25 dots because we have 5 on the rows, 5 dots on the bottom, 5 dots on the top. What would the next one be without drawing it? 36, and the next one would be 49. Now, this is not arithmetic or geometric, but you recognize the pattern, right? What's the pattern? Okay, so we're multiplying this, and what did you just say?
The base squared.
The base squared. And if we call this n equal 1, and this is n equal to 2, like the number of terms that we're on, and this is n equal to 3, the fourth one and the fifth one, we could also say that this is n squared, if these are my n values. Now, I'm not going to ask you to come up with generalized formulas for anything but the arithmetic and geometric, but I think this one, as you're looking at it, almost just felt like you almost needed to see that it did that. And it kind of is nice, right? Because this says these are square numbers, and what do you see down here? It's a square of a number, right? So this makes sense. Any questions on that one? Okay, last slide. This is a real life thing that happened. Real life. In the fall of 2011, the newly formed Hurley College of Science and Math had a meeting. On the board, the value 3.1415 was placed, and we were asked to find the next terms in the sequence of numbers. So without talking to anyone else, I want you to look at that as though it's, a sequence of numbers. What would you say are the next 2 numbers in the sequence? So write down what your guess is are the next 2 numbers in the sequence. All right. What do you think? 1, 6. So if you're doing 1, 6, what are you seeing? Why are you suggesting 1, 6?
The 1 is every other time, and then the 4, and then 5.
Seem realistic? Did anybody else write anything else down? Nobody else did?
I thought it might be 5.
And we were in a room with science and math people. So most of us did this because of exactly what Katrina said. We looked at 3.1415 and our minds automatically went to another sequence that we know. The sequence of numbers that is an approximation for pi. I bring this up because I want you to recognize that what we're doing, and we talked about this last time, is inductive reasoning. We're making a conjecture based on previous knowledge, right? So when I look at that sequence, my previous knowledge says, oh my goodness, that's pi. Got to be the next 2 numbers, 9, 2. You guys weren't thinking anything about pi, and in part because we were looking at patterns in a different way all throughout this section, right? That's part of why. And so your mind was thinking about other patterns in different ways. So this conjecture that you made and the conjecture that I made were 2 different conjectures, and they're both equally valid based on our previous knowledge. There's not a right or there's not a wrong because of that. Interesting, right? I want you to keep that in mind. That's what happens with inductive reasoning, is that sometimes it leads us to different places and we have different guesses that come about as a result of that.